So in section 2.2, we want to describe the behavior of functions. So what we're going to talk about now is when we're looking at a graph of a function, we want to be able to describe whether the function is increasing, decreasing, or constant. And if we're told a function is increasing, decreasing, or constant, we should be able to make a rough sketch of what that might look like. So we read the graph from left to right, and what we're describing here is the behavior of the y values. So if the graph is rising from left to right, we say it's increasing. If it's decreasing, we say the graph is falling. And if it's constant, we say the graph is horizontal. A turning point is where it changes from increasing to decreasing or decreasing to increasing. And so we've actually got a visual here to help read this. So we always read from left to right, and we can see the graph is falling, right, decreasing, then it turns, starts increasing again, then it turns again, starts decreasing, and then it makes another turn and starts increasing. So this graph has 3 turning points, and if we actually had an X scale down here, we could describe the intervals where it's decreasing, right, and the intervals where it's increasing. Another attribute of a graph that we like to talk about is its concavity. So we say a function's concave up if it bends upward. So you can kind of imagine if that section of the graph would hold water, if it rained down from above. If it bends downward or would shed water, we call that concave down. And just like we have a turning point that changes increasing to decreasing, we call the change in concavity an inflection point. So down here you can see, right, we're concave down, we're concave up, we're concave down, and these 2 little dots here are actually your inflection points. Right? And so this is where the graph is changing, right, from concave down to concave up, and then it changes back to concave down again. So let's look at an example. So we have the following graph, and we want to answer these questions. And the first thing I want to know is, where is the graph increasing, decreasing, or constant? So if we just want to know about increasing and decreasing, we can do these sort of together. So I'm going to read this graph from left to right, and when I start from the left, we always, when we give interval notation, we're giving the x values for this behavior, not the y values. So the first x value I encounter is -4. And I can see that the graph is rising from that point. So we're going to say it's increasing, -4 is included. So it's increasing from -4 until it gets to -2. And at -2, where we have a turning point, we use parentheses because the graph is neither increasing nor decreasing there. However, if you're a little careless with that, on the test, try not to be. Some of the instructors are a little more forgiving than others on that point, but technically speaking, we would say the graph is neither increasing or decreasing. Then we see from -2 to -1, the graph is falling. So it's decreasing from -2 to -1. Now, there's actually 2 reasons, right, we would not include -2 here. One, we don't include the turning point in increasing or decreasing, but also the graph didn't even exist there. So you can't have a value, right, that doesn't even exist on your graph. Notice here, the graph didn't exist here or here, so I wasn't able to include either endpoint. Then the graph picks back up at -1, and it starts increasing again. So I'm going to use a union, and I'm going to add this interval of the graph to my increasing. So it does exist at -1, but when I get to 1, it's sort of like a turning point again. It's neither increasing nor decreasing. So this one's sort of a judgment call. You could put a bracket here. You might want to put parentheses, but for good measure, I would actually say it's neither at that location. So then we see from 1 to 5, it's decreasing, but it's still decreasing, right, from 5 to 6. So just because it changes shape, it's still falling. So we would say, well, from 1 all the way to 6, the graph is decreasing. From 6 to 7, it's rising, and from 7 all the way to 9. So once again, even though it's changing shape, it's still decreasing all the way. So, or still increasing all the way. So we would add the interval 6 to 9 to our increasing row. Then from 9 to 11, it's decreasing again. So from 9 to 11. And actually we would include 11 because it does exist at that endpoint and it's technically decreasing all the way to there. So we were also asked, is it constant anywhere? And so our definition of constant is if the graph has a horizontal or the slope is 0 when read from left to right. So we didn't really have any like horizontal sections of the graph. So we would actually say there weren't any constant pieces, but that's what we mean when every single y value is the same across that portion. All right, so now we want to find out, well, where's the graph concave up or concave down? So concavity, the graph has to curve, okay? So if we set up a row for concave up and set up a row for concave down, we can see that the graph is concave down, right, from here to here. Now the issue is we have to remove this point because it doesn't exist here. So the way we would write this is we would say, well, from -4 to -2, and then from -2 to -1, the graph is concave down. So I can't include this because there is a gap there. The function doesn't exist. Now look at these straightaways. Right? There is no concavity here. Even though it's like this jutted corner, it's not bending, right? It's actually making a sharp kind of turn. So we would not say this is concave up or concave down. But when we get here, we can clearly see this graph is concave up from 5 to 7. So we would say from 5 to 7, it's concave up, and then it goes concave down again from 7 to 11. So here's the issue. What do I do about 5, right? And what do I do about 7, right? So notice here, I did not include 7 in concave up, and I did not include 7 in the concave down, because it can only belong to one or the other. So if you say that it's concave up here, well then the graph picks right back up there and then turns concave down. So this is actually an inflection point. So in the same way turning points are neither increasing or decreasing, inflection points are when it's changing concavity, so we do not include those in our intervals. So where are the locations of any local maxima, local minima, or inflection points? So let's look at the maxima first. So we want to list out the maxima, any minima, and any inflection points. So local max and minima really are the same thing as saying turning points. So what we're talking about here are turning points, and we check the end behavior. Of the graph. So let's see what we mean. So let's deal with the maximums first. So this graph comes up, right, bends, and comes around. So there's actually, it looks like a maximum here, right? However, the graph doesn't exist there. So I would not call this a local maxima. If this line were solid all the way around, then we would say we have a local maxima there. But the graph approaches this value from both sides and never quite gets there. So I would be hesitant to list this. However, the graph comes up and turns and goes down. So in this little region of the graph, and this is the way what we call it local max or min, in this little region of the graph, that is the highest y value. Once again, though, we're asking where do these exist, so we're going to list the x value. So we would say that we have a maxima at x equals 1. Then as we come down, right, the graph is falling, comes down, right, starts increasing again, and then it has another turning point. So once again, if I were to look at this region of the graph, we can see that that is the highest point in that area of the graph. So this is at x equals 9, so I would say that there is a maxima at 9, right? Minima, we also want to check the end behavior. So if we look at this at the end here, well, this is the lowest y value in this region. So it doesn't just have to be a turning point. We can also check the endpoints. If this graph had run off to negative infinity, then we would not call it a local minima. So this is at x equals -4. Once again, the graph comes around. We have another endpoint, but the graph doesn't exist there, so I would not include it. However, at this location here, this is the lowest y value on the graph because y doesn't exist down here. So I would call x equals -1 a minima. So it's not because of this, it's because of this. Then the graph falls, comes down and turns. So right here, this is the lowest point on this section of the graph, and that occurs at 6. And then the graph comes around, and we see that it's decreasing, and in this little area of the graph, this is our lowest value. So I would also say there's one at 11. So -4, -1, 6, and 11. So then we have to find our inflection points. So the inflection points occur wherever we have a change in concavity. So if we look back at our graph, right, we can see here that the graph is concave down, right? There's no concavity here. The graph is concave up and then becomes concave down. So this is the only inflection point on the graph. And so we would say we have an inflection point at x equals 7.